I'm going to talk about a background and motivation, then we're going to talk about what the solution is, and finally, what are the benefits and key takeaway for the solution. So as you all probably know, most of the modern data centers are leaf spine fabric class based. They run some form of a layer 3 protocol. Most of them have converged upon BGP. It's very well documented by Peter Lapuko's RFC. And the goals for the control plane as well as the DC class is fairly simple. It should scale, should be extremely simple, and it should be resilient. As you start to build the next gen class networks, you'd see that with more dense port densities that are available on spine, you're going to see more and more ECMP scale coming out. The class tiers would be growing as well, and finally, support for new applications is going to be there. So then, if you're going to use BGP, some of the key attributes of the protocols are, well, it'll support multi-tier, which means it'll do hop-by-hop peering across the class fabric. As a result of hop-by-hop peering, and because of the fact that the spines will be more and more denser, and as you see more and more ECMP scale, it'll have a direct correlation on the configuration. You'll see a config explosion happening. Again, the routing will be hop-by-hop. And lastly, from a BFD link liveness perspective, BFD will be used. So if you look at a class fabric and you compare IGPs and you compare BGPs, here are the positives and negatives of IGPs versus BGP. Well, for IGPs, it's quite obvious that it computes the entire fabric topology at each and every node, therefore has a faster convergence. Does flood a lot of state unnecessarily, maybe, and there is a complexity in the state machine that is involved in there. On the other hand, if you look at BGP, it's fairly operationally well understood and therefore simple. It supports incremental updates, no flooding, and does selective filtering. Also runs on TCP, so it provides a reliable transport. Can do very efficiently per hop, TE, specifically unequal cost multipaths if you need. From a convergence perspective, you would see that compared to a Dijkstra, it's a little bit slower. And as you see a denser spines coming out in the market, you're going to see the config explosion that's going to happen. So if you take all the positives of IGPs and you take all the positives of the BGP and you combine together, what you get is LSVR. In other words, you take the distance vector algorithm out, retain all the update announcements within BGP, replace the distance vector with Dijkstra, you have an LSVR, is what we call as link state vector routing. Some highlights of that, well, it can support multiple tiers. Typically now, when you do this kind of a change, you can facilitate insertion of route controllers or route reflectors within eBGP or iBGP class. What it means is that your peering shifts, and it gives you an opportunity to shift your point-to-point, hop-by-hop peering to the route reflector-like models. And therefore, your configuration now is directly proportional to number of the route controllers or route reflectors that you would end up deploying and not ECMP. This is a great way to break the configuration of the ECMP scale. More importantly, the switches or the boxes within the class fabric can do a distributed SPF computation, and therefore you leave the computation to the switches itself. All the overlay SAFIs, including EVPNs, can follow the same model. And lastly, if you want to do link layer liveness, you still use BFD for that. So then, it supports flexible operational models as described here. You could have a centralized node in your class, regardless of what tiers or how many tiers the class can support. And that centralized node can do both path computation as well as route announcements. It's very ideal if you want to do TE-like applications. Or you could have a distributed path computation where you have a centralized node which will simply reflect the routes or updates, if you will, and the Dijkstra is performed at each and every node in a distributed fashion. And last but not the least, it also facilitates the model where you can have these computation nodes inline, residing on the spines and doing the same functionality, business as usual. So then there's a little bit about the protocol here. It's a new SAFI within BGP. Of course, it supports new capability and a new node attribute to assure compatibility. Supports multiple peering models, as I talked about. And last but not the least, it replaces best path decision process with Dijkstra. From the best path changes, since the Dijkstra has been placed in here, you don't need to honor the next hop and the path attributes that are announced and apply it. However, since the base protocol does require you to announce it, it just announces it and ignores it upon the reset of the update. The decision processes are replaced with Dijkstra. You need to assure most recent version of updates been announced. BGP does this anyways. You use it with the sequence numbers here that are been inserted. From an SPF perspective, it's a greatly simplified SPF, not that it cannot support the advanced version. The first version of the proposal wanted to get the proposal to work very well, scales very well with most of the cases. You could easily do a LFAs. Support for segment routing SIDs is already there. The new SAFI uses LS as an address family format, which has the formats included, so you don't have to worry about it. It's just a matter of extending it. The link state address family also supports dual AFs, both for V4 and V6. As a result of that, both the underlay address families are pretty well defined here. You need, some work is needed to define what happens when you have a base IPv4 enable and you have this particular extension that exchanges IPv4 routes, and it's a matter of local policies. You could tune your network to figure out which SAFI takes the preference and precedence over the other SAFIs, and it should work fairly well. From the fabric standpoint, then the question is, how do you originate the route? You would originate routes either by doing redistribution, something very similar to redistribution connected, or you can use a new protocol that's again worked upon in LSVR working group. It's called L3DL. Its job is to discover unique endpoints and identities for port and link, including its IP address, MAC, label binding. The uniqueness about this protocol is that it has layer 2 keep alive sessions to make sure that the protocol is up almost all the time, kind of like how BGP works, which is session oriented. And the beauty of that approach is anything that you announce from server, let's say, for example, to the TORs, you don't need to age them out. You can hold them as long as session is up. It can also carry configuration information. The standards, like I said, is worked out in LSVR working group. There is an effort to get an open source implementation of this protocol out, which would be highly beneficial both for the servers as well as for the fabric in itself. From the convergence standpoint, it's pretty sleek. The protocol has developed a couple of new TLVs. Their job is to make sure that anytime a link is signaled down or a prefix is signaled unavailable, you basically announce that ahead of withdrawing the necessary LSAs, equivalent of that inside BGP updates, so that you facilitate fast convergence. There is a tunable implicit withdrawal timer as well that avoids unnecessary flooding of the packets. Again, the link level liveness is done using PFT. So, final key takeaways, it's a pretty solid extension for clause. It lets you decouple your hop by hop peering, and therefore allows you to scale in terms of ECMPs as the next gen boxes come around. More importantly, it helps you shrink your configuration files from protocol perspective. Of course, enables through this process a centralized route controller like architectures where you can do efficient traffic engineering. And when it combines with newer solutions like EVPN, it enables full automation, programmability, and resiliency. And last but not the least, when you combine with LSOE, L3DL like protocols, it gives you a full fabric and lets you facilitate faster route origination as well as building of a complete fabric. So that's all I have. Questions?
Michael Kartolishvili, SilkNet. As I looked into the subject, there are quite an effort of also adapting existing link state IGPs, like modifying flooding algorithms. There are quite a lot of drafts from one hand, and on the other hand there is Rift that is also well developed and built from the scratch for this topology. What is the advantage of your solution to be compared with theirs?
Fairly simple. I would say when I look at the class topologies today, 99%, I want to make a bold comment that probably top 90 plus, maybe 99% of this class runs BGP. If you deploy something new, there is a operational cost of deploying it, and this is realized by operators. If you deploy something on top of what is existing today, kind of like BGP, all your operational costs are taken care of, and the new costs that you realize are fairly incremental, at which point you will ask, if I take a debt on this incremental cost, what is it to my network? And what it gives you is scale. It gives you complete control. It lets you take your inbound peering out, shrinks your configuration files, therefore lets your class grow as you want, and the next generation class will grow even more. Helps you build programmability. So these are the things you want to do. And if you could reduce it with a leaner and meaner software stacks, by that I mean single protocol, you want to do that. And that is what it gives.
I just want to add that the protocol that you proposed is, I think, more than 30% of the original BGP. That it changes the best path selection algorithm. There is also new neighbor discovery protocol in addition to avoid the manual configuration, and that can be considered that as a new protocol as well. And also, you in the name of the protocol don't mention BGP, and that's correct, I think. Isn't it so?
So I would say the transport semantics of BGP are in place, which means all your operational tools that do TCP dump-like features and look at the protocol packets, analyze them, are all available to you. Since you deploy, or since SAFIs like BGP LS have become standardized, this protocol format, while we define a new SAFI, uses packet formats which are very similar to LS, which means had you had operationalized LS, had you had operationalized BGP as is in your class, for you to operationalize some of these protocols, protocol extensions are pretty incremental. Now that we have done that with the new set of last mile protocols that are being worked within LSPR working group like L3DL, there is an effort to open source that so that you can take the software and it helps you bootstrap and operationalize it even faster because you have a source code to it. You have a complete control to it. And if you don't want to do that, I think the vendors will come around and give you knobs to simply do equivalent of redistribute connected, source these routes inside this new protocol and build a fabric out of it. So I would argue that the costs are fairly incremental, although I have not used the name BGP.
Thank you.
You're welcome. Thank you.